today. I would like to, it's my real delight to be welcoming Dr. Laura Keating to be our speaker today. Dr. Keating got her BA from Trinity College in Dublin and then moved on to Cambridge, where she got her master's and her PhD, working on absorption line probes at the high-redshift intergalactic medium. And from there, then came over to Canada, where a whole bunch of us got to know her, interact with her in a very stimulating way. People from McGill working at CETA with Laura and vice versa. And so at CETA, she was a prize postdoc fellow, and since then has moved on to the Leibniz Institute for Astrophysics in Potsdam, where she's a Marie Curie fellow. And so today, what we are going to hear about is constraining the reionization history with quasar absorption lines. And Dr. Keating has said, like, if you've got quick clarification questions, you can absolutely feel free to interrupt and ask questions along the way. If we've got, big substantive discussions, we can leave them towards the end. And, we'll be monitoring chat. So we'll also play traffic cop along the way. So welcome and take it away, please.
Okay, great. Thank you so much for inviting me here to speak, and thanks especially for shifting the time of the seminar to suit me. I really appreciate it. So yeah, as Adrian said, today I want to tell you about some of my research, trying to understand what is the timing of reionization based on what we can learn from quasar absorption lines. And so first of all, what is reionization? Well, when we look at this kind of cartoon picture of the history of the universe, if we start over here on the left-hand side, we start off with, inflation and the Big Bang, and then we enter this period where, we see the CMB emitted during recombination. And after that, for a long time, there's not a lot going on in the universe. Everything is very dark and it's very cold. But when the first stars and galaxies start to form, they emit ionizing photons that can heat up and ionize their surroundings. And we start to get these little bubbles or pockets of ionized gas surrounding these first structures. And as more and more of these stars and galaxies form, these bubbles get bigger and bigger, and eventually they start to overlap. And we kind of transition from a regime where everything is neutral and cold to one where everything is warm and ionized. And that's shown here in this image. So everything that's neutral and cold is kind of black, and the warm and ionized stuff is kind of a lighter purple. And so this process of moving from, neutral to ionized is known as the epoch of reionization. And so although we have this kind of cartoon picture of what reionization is, everything started off neutral. We know today at redshift 0, everything is ionized, and somewhere in between it all happened. But there's still questions that we would want to answer about this. And specifically, we want to know the when of it. So when exactly did this process occur? On this kind of cartoon picture, we have, it happened between, redshift 6 and 15 ? But can we do better in that? And we want to do better in that and kind of learn about this period in the history of the universe. And the second question is the who. So what exactly are the sources that ionize the universe? I've already mentioned that it was probably driven by stars and galaxies, but was, for example, there also a contribution from AGN? We know there's quasars out above redshift 7. Do they have a role to play in this? And finally, the how. What is kind of the topology of reionization? What are the shapes and sizes of these ionized bubbles? Are they mainly small and driven by low mass galaxies, or are they driven by larger galaxies and therefore have larger bubbles? So these are the questions we would really want to answer to get a full understanding of the picture of reionization. But why do we want this picture of reionization in the first place? Why do we care? Well, I think kind of there's two main reasons. Either maybe you're very interested in kind of the astrophysics of it all. And in that case, learning about reionization is interesting because it gives you an insight into the first galaxies and black holes. And an example of how this might work is shown in this plot here, which shows the evolution of the IgM neutral fraction. So how neutral the gas is. So if it's at 1 here, it will be completely neutral, and 0 is completely ionized, as a function of redshift. So these curves start off neutral and slowly become ionized. And the difference between the purple and the blue lines here are what you assume about the properties of the galaxies that drove reionization. In this blue line, it's mainly driven by low mass galaxies, and you have this kind of extended reionization period. Where in the purple line, it's driven by higher mass galaxies, and it's a lot more rapid. So by studying reionization, we can maybe learn something about the star formation efficiency or the escape fraction of these galaxies. On the other side, you might not really care about astrophysics at all, but you might care about cosmology and understanding kind of the fundamental parameters of our universe. And one of the ways you can do that is by studying the Lyman-alpha forest and trying to use this as a cosmological probe. But the Lyman-alpha forest is very sensitive to the thermal state of the gas and also its ionization state. And in particular, the timing of reionization can change the shape of this flux power spectrum of the Lyman-alpha forest, where depending on the timing of reionization, you can get this excess power on the largest scales. So to really exploit the Lyman-alpha forest as a cosmological tool, you would always also want a complete understanding of reionization. And of course, this is a really exciting time to be working on reionization. There's a lot of facilities that are now producing their first results, like Hera, ones that are in the pipeline, like SKA, and obviously soon to launch is JWST. And with these instruments, we're really going to have a whole new view of both the timing and the sources of reionization. And in particular with James Webb, we'll really be able to hopefully characterize what are the sources that drove this reionization process. But while we wait for these really exciting results, what I want to talk to you about today is what can we learn about reionization from the data that we already have now? And I hope to show you that we can learn quite a lot. And so first of all, kind of what do we know about reionization already and its timing? Well, some of the tightest constraints come from the cosmic microwave background, and in particular from Planck. And when we look at photons coming from the CMB, they can scatter off free electrons, and you can calculate what is the optical depth of the scattering, which gives you an estimate of how many electrons there are in the line of sight between us and the CMB. And you can translate this into a constraint on the timing of reionization. And in particular, it's most sensitive to when was the intergalactic medium about 50% ionized. And so what's shown in this plot here with the colored lines is the electron fraction as a function of redshift. So here, when the electron fraction is 1 or greater than 1 after helium reionization, everything is ionized, and when it's 0, it's neutral. And each of these colored lines is just an example of a different reionization history. So some are very sharp, some are very extended, some even have more than one peak. But all of these will give you the same optical depth to reionization, but where they really overlap is around the midpoint. So that's what the CMB is telling you. There's also another tool that you can use to see how much neutral gas you have in your intergalactic medium, and that's scattering of Lyman-alpha photons. So if I have this cartoon picture here of a neutral hydrogen atom, if my Lyman-alpha photon comes in, it can excite the electron in the first energy level up one. And then when that electron decays back down to the previous energy level, it will emit the Lyman-alpha photon. But crucially, it won't emit, it's very unlikely to emit it in the same line of sight that it originally entered in. So if I'm looking at Lyman-alpha coming from a distant galaxy or quasar, to me, it will look, when this scattering process happens, it will look like it's been completely absorbed. So I will no longer see this Lyman-alpha photon if I've encountered some neutral gas. And you can look at the Lyman-alpha emission coming from galaxies and try and turn that into a constraint on how neutral the intergalactic medium must be as a function of redshift. And there's just a couple of plots here that shows how this is done. So the first one is I can look at a bunch of galaxies and I can ask, well, in this large survey, what fraction of all my galaxies show Lyman-alpha emission? And I can do that in a different few redshift bins. So you can see from redshift 4 to 6, more and more of my galaxies are showing Lyman-alpha emission. And this is generally because as you move to higher redshift, there's less dust, so you see Lyman-alpha more. But once I get to redshift 6, something funny happens, and all of a sudden, my Lyman-alpha emission starts becoming more and more rare. And this is unlikely to be, it's hard to think of a property of the galaxies that would do this. So maybe instead it's a property of the gas around the galaxies, that it's becoming more neutral, and that we're starting to see into this reionization process, that the neutral gas is scattering away this Lyman-alpha emission, and it's hard to see. Another way I can look at it is, rather than by looking at continuum selected galaxies and seeing if they show Lyman-alpha, I can just look directly for Lyman-alpha emitting galaxies and select them that way. And so what's plotted here on this plot on the right is a Lyman-alpha emitter luminosity function in different redshift bins. And if you just focus on the red and the blue lines here, these are Lyman-alpha emitter luminosity functions at redshift 5.7 and 6.6. And you can see at the brightest end, there's not much evolution, but there's a lot of evolution at the faint end. And it's quite rapid, and it's maybe a sign again that we're seeing this evolution in the Lyman-alpha properties of the galaxies, and maybe again it's a sign of this neutral gas that's becoming more and more important at high redshift. And so both of these effects seem to kick in at about redshift 6. So we see it here in the continuous selected galaxies and also in the Lyman-alpha emitters. So that would maybe suggest that reionization is over by about redshift 6. But what I really want to talk about today is about Lyman-alpha absorption seen in the spectra of the highest redshift quasars. And so if I have an example of, this is just a cartoon of how the Lyman-alpha forest is generated. But if I have if I have a spectrum of a quasar here, I have this peak at 1216 angstroms, which is the Lyman-alpha transmission of the quasar. And on top here, I just have a cartoon of light traveling from the quasar to us, the observer, which would be over on the right. And the arrow is kind of the current position of the light. And so as this arrow moves, every time you interact with some neutral gas, you get an absorption line feature in the spectrum of this quasar. And so these absorption lines are a really powerful probe, not only of large scale structure, but of the neutral hydrogen contained in these galaxies and filaments. And you build up this Lyman-alpha forest of lines, so it's called, that you can use to do lots of statistics and learn not only about astrophysics, but also, as I already said, cosmology. And so this is just, again, showing the same thing, that at low redshift, so this is around redshift 3 or so, you can identify individual absorption lines in the spectra of these objects and use them to do all sorts of statistics. But unfortunately, as you move to higher redshift, this becomes more and more difficult. So this is now an example of a spectrum at redshift 6. And so here I have my Lyman-alpha peak, and you can see there's still a lot of transmitted flux even below that. Whereas here, this is my Lyman-alpha peak, and you can see it really rapidly drops off, and to the point where almost no flux is transmitted in the region close to the quasar, just because at higher redshift, things are becoming a bit more neutral and a bit denser, and it's easier for the Lyman-alpha photons to scatter. So instead of having this forest of individual absorption lines that I can study and do cosmology with, I don't really have any forest at all. What I still have is just a few odd transmission spikes in the regions where there's not so many absorption lines superimposed. And so it becomes harder and harder to use these absorption lines as a tracer of what's happening, but we give it our best shot anyway. And so although you can't do the individual analysis of these absorption lines, you can still just kind of broadly look at these objects and say, okay, well, here's a collection of quasars going from redshift 6 up to 6.5. And you can make, some statements about them. So, once I get beyond redshift 6, many of these objects don't show any Lyman-alpha forest at all. All the flux is completely absorbed. And below redshift 6, you do see, some transmitted flux. So again, as with the Lyman-alpha emitting galaxies, you can play the same sort of game that, below redshift 6, we see this Lyman-alpha, above it starts to fall off. So is this again a sign that around redshift 6, kind of magic number, is this the end of reionization? Well, hang on. Because at the same redshift, if you look at some of these objects, the Lyman-alpha forest can look really different. So this is an example of two quasars at the same redshift. So the redshift range is shown on the top axis here. And they're just two quasars, on different parts of the sky. So probing different parts of the intergalactic medium. So at the same kind of point in the universe's timeline, but spatially separated. And they have were chosen to have similar signal to noise. So any differences you see here are like an actual property of the intergalactic medium at these redshifts. And what you see in this black quasar is that I have quite a lot of these absorption spikes. So I seem to be probing a part of the intergalactic medium that could be quite ionized. Whereas in this red object, for 160 megaparsecs, I don't see any significant transmitted flux at all. Even though this is kind of at the same point in the history of the universe, there's quite astonishing diversity between these two objects. And so the first thing you could think of is, well, are we just seeing evidence of reionization? Is this just one long bit of neutral gas that this sightline is intersecting with? Because it's hard to think of what other structure could be 160 megaparsecs long. But if I look not only at Lyman-alpha, but Lyman-beta along this object, and Lyman-beta has a lower atomic oscillator strength, so it doesn't need as high a column density of neutral hydrogen to be completely absorbed, so you can still see it even if the gas is only weakly ionized. And in fact, we do see Lyman beta transmission along this same sightline. So here the black is the same as the red. And these blue spikes are all these Lyman beta transmission spikes. So this can't be just one piece of completely neutral gas. So what's going on here then? And so we can try and be a bit more statistically sound rather than just saying, hey, these look different. We can actually go and try and put some statistic on this. And generally, we talk about the effect of optical depth in some segment of these sightlines. And so this is basically you go and you measure within a 50 megaparsec section of your spectrum, what is the mean flux? And then you convert that into an effective optical depth using the usual equation. And so you can make a plot like this, which shows the evolution of this effective optical depth as a function of redshift. And so here, when I have a low effective optical depth, that means the mean flux in my object is very high. So I see a lot of transmitted flux, meaning the gas is kind of ionized. And when my effective optical depth is high, I don't see so much flux. So the very absorbed sightline that I showed before would have a very high effective optical depth. And so there's two things to notice in this plot. One is that generally the effective optical depth is becoming higher as you move to high redshift. And that's the same as saying when we look at these high redshift objects, we see less and less of a Lyman-alpha forest as we move to high redshift, which I've already said. And the other thing to notice is the scatter in this quantity is also increasing with redshift. So at redshift 4, I have a very tight scatter in my effective optical depth. And what that's basically telling me is if I look at different objects along spatially separated in the sky, they basically all look the same statistically. But if I move to higher redshift, my scatter increases dramatically. And so that some of my objects will have this very low effective optical depth and some very high. So this just means I have a very large diversity of objects at this redshift. And so is this a signature of reionization? What's going on? I can also, rather than just doing a scatter plot, I can plot the cumulative distribution function of these objects in different redshift bins. And again, this says the same thing, that at low redshift, I have this tight scatter, and at higher redshift, I have a much longer scatter. And what's kind of important to quantify is the scatter at high redshift is much larger than that's expected for any fluctuation you would get in your density field. So at low redshift, I have this small scatter, and that's pretty well reproduced by this yellow dashed line, which is what I get just from taking lines of sight through a cosmological simulation and measuring this quantity. So sometimes you hit a very overdense region and sometimes you hit a void, and that's enough to explain the difference. But as I move to higher and higher redshift, I start to see this kind of peeling off of the cumulative distribution function, where I get this long tail that's no longer explained by the density field. And you can kind of start to see this kick in, definitely by redshift 5.1, and certainly by redshift 5.7. So whatever this is causing this discrepancy, it's not just the density field, it's something else. So then the question is, well, we have this effect, and it seems to be kicking in at around the same redshift where we see reionization. So can we learn something about reionization from this data? So I can think about, well, I have my Lyman-alpha forest, and that's sensitive to how much neutral hydrogen I have in my intergalactic medium. And so if I just assume everything's in photoionization equilibrium, kind of what knobs do I have to turn? Well, I can write down, I can balance my recombination rate against my photoionization rate. And my recombination rate depends on the temperature, and my photoionization rate also enters here. And then I also have this density squared term, but I've already said the density field doesn't explain this effect. So that basically leaves me with two things I can look at. Either there's some change in the temperature on large scales, or there's some change in the ionizing background. And there's reasons you might expect either of these. But just to first show you what effect this would have on the Lyman-alpha forest. So on the top panel here, or these are two just mock Lyman-alpha forest spectra from a simulation. And the top panel, I'll show you what happens when I change the UV background, and on the bottom, what happens when I change the temperature. And so if I make my UV background smaller, or if I make my gas colder, I get broadly the same effect, that I get lower flux. Whereas if I make it more higher ionizing background or hotter gas, then I get more flux. So these, have roughly the same effect, whichever knob I turn. So why would we expect this effect to happen? Well, if I think about why I might expect the UV background to fluctuate, well, we know if we have a density field that there's clustering of sources. And so if that will give you to first order some fluctuations in the UV background. But you can also amplify this effect if you assume that either the mean free path is very short, or if it fluctuates based on where the distribution of absorbers as well as sources. And so this was proposed by Fred Davies, who's now at Heidelberg. And this you can implement a model like this, and you're able to explain this diversity of the Lyman-alpha forest. You can also, as I said, try and come up with some reason your temperature might fluctuate. And this also occurs very naturally as a consequence of reionization. If I have areas of the intergalactic medium that reionized early on, as the gas was ionized, it was photoheated. And since it was ionized, it then has time to cool down. So if I look at, say, this blue curve at redshift 12, if it was ionized then, it gets heated, 3 times 10 to the 4 Kelvin, and then it starts to cool down. Whereas if I have another region of the intergalactic medium that reionized towards the end of reionization at redshift 6, that will heat up and will have time to cool down, but not as much time as the stuff that was ionized early on. So if I look at all this gas that was ionized at different redshifts, at a single redshift, say at redshift 5, I can get scatter in my temperature field just based on this large-scale distribution of bubbles. So both of these effects are plausible. And so what we decided was, well, we wanted to run some cosmological radiative transfer simulations that potentially would contain both of these effects, that maybe we could learn which was dominant and say something about what's going on. So we set out to do this, and we use a very fast GPU-based code, which we use to post-process cosmological simulations. And so this means we can run these simulations very quickly, and we can tune exactly when we want reionization to happen by changing the emissivity of our sources in the box, which is a free parameter. And so we can run one of these simulations, and that ends at about redshift 6, and we can compare it to the data that I'm showing here. So these are these same distributions of effective optical depths that I showed before, now with some kind of error range on the more uncertain sightlines. So the blue is the observation. So what do our simulations look like? And so that's the orange. And so you can see, you sort of get reasonable shapes at low redshift, although there is an offset. And you start to maybe see a hint of a tail as you move to higher redshift. But generally, the agreement isn't good. At redshift, 5.3 and 5.7, we don't get any of these really dark sightlines in this model where reionization finishes at redshift 6. So we tried to think about what was going on. And we had kind of been calibrating these observations to match the photoionization rate, which is shown in this plot here, the observations of it. And when you look at the photoionization rate, it's pretty flat out to about redshift 5. And then it rapidly turns over as you move to redshift 6. Again, this kind of maybe again signal that reionization is ending then. But if I actually go to my simulations and I ask, what is the mean flux of the Lyman-alpha forest at these redshifts, which is what the photoionization rate is derived from, and I look at that as a function of redshift, I get this yellow line here, which you can see doesn't agree with any of the observations at all at any redshift. And that's because there's this degeneracy between the temperature in our simulations and the ionizing background. So that gives you some kind of freedom to change the photoionization rate that you get. So what if I forget about this photoionization rate and instead tune my simulations to directly match the mean flux? I can do that. And what I find is that now to match the statistics of the Lyman-alpha forest at these redshifts, I need to have a model where reionization ends below redshift 5.5. And in fact, maybe something more like 5.3, 5.2. We also include information from the cosmic microwave background to try and constrain the higher redshift end. So we end up with a model that's about 50% ionized at redshift 5.7 and complete by about redshift 5.3. And so that's kind of our first main result, that to try and match the statistics of the Lyman-alpha forest, you need this late reionization. And so this is kind of exciting because, from looking at these galaxies and from the CMB results, people have always said that reionization must have ended by redshift 6. But in fact, this doesn't seem to be the case. And what's really nice is not only with these simulations can I get the mean flux of the Lyman-alpha forest right, but I also then quite naturally get this evolution of this effective optical depth. So the diversity among all the Lyman-alpha forests along my different lines of sight really nicely falls out. That at lower redshift, redshift 5 and below, I get this kind of tighter correlation that everything looks more or less the same. And as I move above redshift 5.5, my simulated Lyman-alpha or effective optical depth, which is this blue range here, really blows up. And it's easy to understand why this is happening when you look at the evolution of the neutral fraction along a light cone through the volume. So this is just the spatial axis on the y-coordinate and the redshift axis on the x-coordinate. And everything that's blue is ionized and everything that's red is neutral. And so you could imagine having a sight line that passes through the top of the box here and intersects mostly neutral gas kind of below redshift 5.7, redshift 5. And that would give me a lot of transmitted mean flux and a low effective optical depth. Whereas if I have a sight line that's mostly passing through these red neutral islands that exist below redshift 6, that means a lot of my flux is going to be totally absorbed because all my Lyman-alpha photons are being scattered. And that would give me this very high effective optical depth. So this late reionization model very naturally explains all these statistics, and it's a very nice way to do this. And I can also go back to this plot of the cumulative distribution functions, and you can see now that I've tuned my mean to very nicely match kind of 0.5 point, I also really nicely get out the total shape of this distribution function without having to tune for that. So all we tune for is to get the mean right, and the rest of it naturally falls out. So that, is very nice and seems to work very well. But can we test it against any other quantities? So for example, I've already said at the beginning of this talk that you couldn't explain this very long 160 megaparsec trough by just assuming you were hitting a neutral island, because you see this Lyman beta transmission. So at least some of your gas must be ionized. So why is this? So this is the observed spectrum here on this top panel. So we can go into our simulation and we can ask, well, do we see anything that looks like this? And so this is an example of one of our mock spectra taken from the late reionization model. So the black here corresponds to the Lyman-alpha in both cases. And what we see is we do find sight lines where we get these very long absorption troughs, maybe not quite as long as observed, but close, where I have a lot of transmitted flux, in this case below redshift 5.6 or so, and then you don't see anything at all above that. But that's the Lyman-alpha. What about the Lyman beta? So I can go and I can look at my Lyman beta, and very nicely we do see transmission of this, even in the regime where we don't see any Lyman-alpha. And again, it's not a one-to-one correspondence, but it's, more or less the same. So why is this? Why do we see this Lyman beta if we're looking potentially through these large neutral islands? And well, the thing is, these neutral islands aren't completely one object. They're porous, they have little holes, because there can be, a little tiny galaxy within your void that's able to ionize its surroundings. And so I can look at maps of my neutral hydrogen fraction, where again, everything that's blue is ionized and everything is red that's neutral. And this white dashed line here is where I saw the long absorption trough I showed on the previous slide. And you can see that indeed this sight line does intersect with a lot of neutral gas, but it also, there's regions where the gas is ionized. And these are the regions where you see your Lyman beta transmission. But I had already talked at the beginning of the slide of this saying, well, did we expect to see these fluctuations in the ionizing background or in the temperature? So that's what's shown in these two panels here. And we do see that there's fluctuations in both these ionizing background and the temperature, as shown by the lower photoionization rate due to the shadowing of these neutral islands, or these patches of hot gas where the gas is just ionized. So all of these effects are present in our simulations, but really the dominant one is the presence of these neutral islands at lower redshift. So we can also then say, okay, well, that's well and good for the Lyman-alpha forest, but are there any other ways that we can really test this model? And one of them is by one way is by looking for correlations between these very totally absorbed sight lines and to see if there's any galaxies that are around these. So again, this black is our spectrum that I've been showing throughout this talk. And the red line here is a filter on Subaru that you can use to select Lyman-alpha emitting galaxies within this redshift range. So just above redshift 5.7. And what's nice is that these models for either these fluctuations driven by fluctuations in the ionizing background in red, or fluctuations in the temperature field in blue, make very different predictions for whether you should expect to see any galaxies around these very dark sight lines or not. In the case of UV background fluctuations, you expect that these darkest sight lines are living in voids, far away from any clustering of sources. And so you expect that what's shown here is the surface density of Lyman-alpha emitters around your darkest sight line as a function of radius. So very close to the sight line, you should be in the deepest part of the void and not see anything at all. And as you move higher and higher radii away from the center, you expect to kind of return to the mean value. Whereas with my temperature fluctuations, I expect the regions that are darkest to be the ones that are coldest, and therefore the ones that ionized first. And there I expect close to my sight line to see a lot of these Lyman-alpha emitting galaxies. So you expect the opposite effect. And so people went out and they looked for this, and the results are shown as the black points. So it seems that these very dark sight lines want to live in voids. So that's a result for these UV and temperature fluctuation models. But how does this fit in with our neutral islands? Well, so if you think about kind of reionization driven as an inside-out process, then the regions that you expect to be the last to ionize are the voids. And so this also fits in with this picture where you don't expect to see any Lyman-alpha emitting galaxies very close to the sight line. And indeed, that's what we see in our simulations. So what's shown here is a mock map of fake narrowband selected Lyman-alpha emitting galaxies, where the colors are just the magnitude of these objects. And our darkest sight line would be right here in the center of these circles. And so you really don't see any galaxies very close to the sight line, indicating it's living in a void. And likewise, if we make this plot of the surface density as a function of radius, the black points are the observations and the blue are the results from our model. So a very nice agreement. And what's exciting is different groups have gone after this result and using both semi-numeric methods and kind of a Bayesian statistical framework, and also looking at full radiation hydrodynamic simulations and trying to see what are the properties of the Lyman-alpha forest in simulations that ionize at different times. And there's kind of a consensus, I think, building among different groups that to match these properties of the Lyman-alpha forest, you really need to have a significant amount of neutral gas below redshift 6. So I think it's nice that this has kind of now been independently verified by other groups. It's not me just insisting this. And so I couldn't come to kind of McGill without saying something about 21 centimeter. So what does this late end reionization mean for the 21 centimeter signal? So there is a nice paper on this led by Janaki Rast, who compared two different models shown here in this plot of the ionized fraction as a function of redshift. The blue is this late ending model that I've been talking about throughout this talk, compared with the gray dashed line, which is a model that ionizes around redshift 7. And both of these models have Planck optical depths that are kind of within some agreement either with 2015 or 2018 data. But if I look at the evolution of the brightness temperature of these two objects or these two models, I see quite different results. So just looking at the average temperature as a function of redshift, you can obviously see the difference. And also if I look in a light cone and a slice through these models, so again, the spatial axis on the Y plane and the redshift axis on the X plane. And anything that's orange here has a high brightness temperature, and anything that's blue is low. And you can see that in this late reionization model, which is shown in the bottom panel here, there's a lot of this higher brightness temperature gas persisting down to lower redshift, driven by the presence of these neutral islands. And so you can translate this into a power spectrum, and that's what's shown here. So each panel here is a calculation of the power spectrum at different redshifts. So going from redshift 6 down to redshift 5.4. The black line is what you get for this late reionization model, and the gray dashed line is what you get from the early reionization model. So this is reionization ending at 5.3 versus 5.7. And the colored lines here are the noise curves for some different ongoing and future 21 centimeter experiments. And you can see at the largest scales, there's potentially a detectable signal even below redshift 6 for this late reionization model. So this would be very exciting for someone to maybe go and look at. And so kind of what's coming next? Well, we have some really new observations of the high redshift intergalactic medium that we're kind of currently working on analyzing. And so this was part of a large program on the VLT X shooter, which got us a really nice new sample of 30 new quasars at redshift 5.7 at what we call very high signal to noise. So signal to noise around just over 20. And so 30 new objects might not sound like a lot, but to us it really is, because this data set was actually going to be a factor of 4 increase into the number of really high quality spectra we have to do the kind of science that I've been talking about. And so this plot here just shows an example of some of these spectra that was put together by Christina Eilers. And you can see they're kind of been ordered by their emission redshift here. And again, we have this usual really nice diversity between the Lyman-alpha forests of these redshifts. So it's really exciting to start analyzing this data. And so far, we've submitted a couple of papers on it. So the first is just an analysis of kind of a reanalysis of the Lyman-alpha forest with this updated data set. And if I look at the evolution just of the mean flux as a function of redshift, you can really see the power of this new sample. So the previous results we had are all the gray lines here. So you can see there's, discrepancies in measurements between different groups, and the error in some cases can be quite large. And our new sample is now this red data set. So you get a really tight constraint on the mean flux of the Lyman-alpha forest as a function of redshift in a really nice large sample that's been analyzed in a very homogeneous way. So this is going to be very powerful for kind of building our next set of simulations. But you can also look and see how the current set of simulations compare to this new data. So the simulations are in blue and the new observations are in red. And even though these models weren't tuned to reproduce these new observations, you can see in general the agreement is still very nice. And we get, can reproduce at the same time both the brightest and the darkest sightlines. So it'll be very exciting to build on this. We can also move from looking at these kind of core statistics like the mean flux or the mean flux averaged over 50 megaparsec bins, and we can start to do more detailed analysis, actually focusing on individual absorption spikes and lengths of certain troughs in these spectra, thanks to the really high quality of this data. And so this is just one example of a paper led by Young Zhu at UC Riverside, where he's analyzed a bunch of these spectra and he's identified significant transmission spikes in their spectra, shown on the bottom panel here for this object. And so anything that's gray is a region that doesn't have a significant transmission spike. And he measured all the lengths of these gray regions and can plot them as a function of redshift. And you can see, I guess, as we sort of talked about throughout this talk, that as I move above redshift 5.2, 5.3, I start to see significantly large regions of very dark Lyman-alpha forest. So, 30, 40 megaparsecs where I don't see any transmitted flux at all. And so this is kind of a new way of looking at the same data. And you can go and you can compare it again to our simulation. So this is the observed data here on the left. In the middle is a simulation that doesn't contain any reionization fluctuations at all. And on the right is my late reionization model. And again, what we find from looking at this data is you really need this late ending reionization to match not only the total number of these gaps, but also the redshift distribution. So to get some of these gaps below redshift 5.5, you just don't find in this uniform UVB model. So, we're really excited to use this data set to try and come up with different ways to test these models and to hopefully learn more about the specific timing of reionization. And so, I'll just kind of summarize here. So I hope I've convinced you that, if you want to try and match the mean flux of the Lyman-alpha forest, and really like most other statistics you can think of, you really need to have an intergalactic medium that still contains like a significant amount of neutral hydrogen below redshift 6, where significant here means, at redshift 6, neutral fraction should be about 10% or so. And if you look at this model, not only do you naturally reproduce the large spatial fluctuations in the opacity of the Lyman-alpha forest, but you can also get the correlation of these fluctuations with Lyman-alpha emitting galaxies. And excitingly, this late reionization model should predict some 21 centimeter signal even below redshift 6. And we're really excited with these new high quality observations that we've obtained that are that have allowed for higher precision measurements of the Lyman-alpha forest, and that hopefully we can use to more accurately characterize this tail end of reionization. So thank you very much for listening.
All right, thank you very much for a very interesting talk, and I encourage everyone to use their Zoom emojis or to express your appreciation in the chat. So we already have one question, and I'll encourage other people to ask questions as well in the chat, which is these from Professor Robert Brandenburger, which is, all these simulations you talked about, are they all based on lambda CDM Gaussian initial conditions, or do people also do variations on that?
Yeah, so far, all the stuff I've done is lambda CDM. I do have a warm dark matter simulation that's sitting where we have so all of this is done in post-processing. So I have the hydro simulation waiting to be post-processed with my radiative transfer code, but I haven't gotten around to that yet. But I'm excited to see how it looks, with a different assumption for dark matter and whether that's maybe potentially introduces some potential differences, but I haven't looked at it yet. Okay,
great. And I see Jordan has his hand up. So Jordan, if you want to type in the chat or unmute, whatever you prefer.
Yeah, I don't have it fully formulated how I want to ask this question, so I'm going to ramble for a second. Really nice talk, by the way. Super cool stuff, especially like the new samples, really exciting. I was wondering, the initial result of, achieving these big troughs was driven largely by introducing a delay in the overall timing of reionization. I was wondering now, especially with this new sample, if you're thinking about playing with the duration of reionization as well, especially because, these, as I think you said, this temperature effect should be there at some level, and that could indicate variations in the timeline of reionization. And I'm wondering if the new sample is big enough to start teasing out effects like that,
so
I
didn't go into this, but we do have another model where we have the ending of reionization fixed, but as you say, we shift the midpoint, so you get this kind of overall longer reionization. And so what this does is as you move to higher, so the models basically look the same below redshift 6, where they're kind of constrained by the Lyman-alpha forest. But above redshift 6, you can see large differences in the bubble sizes. And so for this late result that I showed here, where we measured these dark gaps, it seems that this is maybe less preferred in this model where we shift the midpoint at the kind of highest end, but there's not a lot of gaps here to measure, so it's kind of not totally certain. But another way that these models look very different is if you count the number of transmission spikes above redshift 6. So that also, because then if you're probing different bubble distributions, you can expect a different number of transmission spikes. But unfortunately, this requires like a lot of high quality quasar data above redshift 6. So you kind of need the quasars to be at redshift 7 or so. So we don't have a lot of those objects yet, but hopefully as new stuff is discovered, maybe with Euclid or you could kind of apply the same sort of technique we're doing at redshift 6. You could push it a bit further and maybe say something about the midpoint of reionization. I think though it is kind of hard because obviously the more neutral you get, the less Lyman-alpha forest you have. So yeah, it's not super sure how far you could push this beyond maybe redshift 6.5 or so.
Okay.
Other questions? Anyone else have questions? If not, I'm actually going to jump in and ask a question that I would like to ask, which is, it's very convenient that you're on this slide. So it's yeah, I think it's really interesting, this idea of the gap distribution, right? But I guess with a 1-point statistic like a gap distribution, you don't care, like you don't care about whether, for example, I have a long gap next to like a bunch of small gaps versus they're distributed in a different way. So is there potentially something to glean along those lines as well? Sort of like a conditional distribution of like, given that I've got a long gap at this redshift versus something else, or yeah, the scale's not right for something like that.
So do you mean like spatially offset or still along the same line of sight?
Still along the same line of sight. But yeah, I mean, spatially offset would be interesting too.
Yeah. Yeah, I guess we haven't really, so far all we've really focused on is kind of, yeah, how many of these gaps do we have? I think, yeah, there probably is more information in how they're, like what their neighbors are doing as well. But yeah, I haven't thought about it, but I think it would be interesting to think about for sure.
Yeah, and I guess sorry, go ahead.
No, so yeah, we've only had this complete data set for, yeah, since the beginning, kind of the end of last year, I guess. So we're still kind of thinking of new and exciting things we can do with it. So for sure, we haven't heard the last of it, and I hope there's a lot more we can get out of it.
Great. Other questions? Any other last questions? Okay. Well, if not, then thank you very much again. We'll let you.
Thank you very much for having me.
And enjoy the rest of your evening. And of course, I'm sure lots of us will be staying in touch with you to hear all about all these